Hello everyone, my name is Konstantin Vladimirov and welcome back to our C++ course. In the previous lectures, when we talked about allocators and smart pointers, we were gradually moving towards today's topic, dynamic polymorphism. This is one of those areas in C++ that people constantly argue about. Many developers try to avoid it. They prefer templates, concepts, static polymorphism, anything that removes virtual functions from the picture. And yet, dynamic polymorphism keeps coming back. So today, we'll try to understand why. What problems does it actually solve? When is it necessary? And when is it better to avoid it? Let's start with motivation. Suppose you, the programmer, have a task where you can choose between static and dynamic polymorphism. You can write a template or you can write a base class with virtual functions, and both are equally well for your task. What do you choose? And of course, the majority answer here will be static polymorphism. That's our default. It's resolved at compile time. There's no runtime dispatch, and it usually gives better performance. So then the question is, why do we even need dynamic polymorphism? If templates are so powerful, what remains uncovered? Pause the video for a moment and think about it. Try to formulate the whole list of cases where we do really need dynamic polymorphism. And I will wait. 3, 2, 1. Okay. I hope it right. Well, one scenario is when you want a common interface and you want to call different implementations indirectly through a base pointer or reference. The caller knows only the interface, not the concrete type. This kind of decoupling often requires runtime support. This bullet. Another case is when a function needs to return different concrete types depending on a runtime condition. Templates cannot branch on runtime values. If the decision is made during execution, the mechanism must also exist in runtime. And finally, like heterogeneous storage. If you want to keep objects of different types in a single container, you inevitably lose static type information. Once the type is erased, templates can no longer help you. You need some runtime mechanism. These are the situations where static polymorphism simply cannot express what you want, at least not directly. And one seemingly obvious example like EOStream we'll analyze later. There is something more subtle going on there. Now let's move on and see how C++ actually implements runtime polymorphism and what trade-offs come with it. And let's look at a very simple example. Extremely simple. We have an abstract base class with a pure virtual function draw and a derived class int t that implements it and draws some integer data. Now, if this were a live audience, I would ask someone to immediately point out mistakes in this slide. And there are two of them, at least two of them, really. There are a lot more. In this slide, there are more mistakes than lines of code. And the most obvious one, please pause the video again, count like 3 to 1 and give me this answer. And yes, of course, the most obvious one, the destructor is not virtual. If we ever delete a derived object through a base pointer, the behavior is undefined. No, maybe not really undefined, well-defined. So sorry, the behavior is well-defined. This deletion is just not polymorphic, yes? The derived part simply won't be destroyed correctly. So if a class is meant to be used polymorphically, its destructor must be virtual. But that's not the only issue. in the derived class, draw is missing the override specifier. And this one is just as important. Why? Because without override, you might accidentally change the signature, maybe forget const, maybe slightly change a parameter type, and instead of overriding the base function, you silently introduce a new overload. The program compiles, everything looks fine, but dynamic dispatch doesn't work. Override is essentially a compile time assertion. I really intend to override something. If don't, fail the compilation. So yes, people usually notice the virtual destructor, but forgetting override is classic bachelor level mistake, and I hope you can point me at least one more in the slide, but let's stop now. I will reveal it much later in the slides. Okay, and now we fix both problems. The base class has a virtual destructor, the derived class marks draw as override. By the way, if the derived class had its own destructor, we would also mark it as override maybe. Maybe not. This is not mandatory. The destructors are special, they all have single signature, but if you override, say it explicitly, if you have this destructor override, then you cannot have this destructor not virtual. And that's a good stuff. And override costs nothing and protects you from very subtle bugs. And now let's briefly recall how this mechanism works under the hood. When an object of the derived class, say D, is constructed, the compiler initializes a hidden pointer, the so-called VPTR, virtual table pointer. That pointer refers to a virtual table corresponding to the dynamic type of the object. Even if we store the object in the base pointer like here, the VPTR still points to the table of derived, So when we call b arrow draw, the call is resolved through the virtual table and the derived implementation is invoked. This is runtime dispatch. And of course, we expect this mechanism to have a cost. Here is typical situation. We create a derived object, we bind a base pointer to it, and at first glance, b draw is in an indirect call. The function address is loaded from the virtual table and then invoked indirectly. The load itself is global variable access. And then, after that access, you also make indirect call. Are we scared? And please remember lecture on allocators, yes? When we talked about polymorphic allocators, we weren't scared. But that sounds expensive. Is it always expensive? And the truth is, it is not necessarily expensive. In the best case, the compiler can devirtualize the call if it can prove that the dynamic type is known at the call site. For example, the object is local and not escaped. It may replace the virtual call to a direct one, no indirection at all. And modern compilers are surprisingly good at this. Let me show you an example from this slide. You can see here the same example with base, derived, and with call that calls b.foo. And here we're calling bus of D. And what do we see here? We see here indirect access inside call, and we see here indirect call inside and we see here indirect call direct call inside bar. Okay, please look one more time. here. Here we statically know the type derived of D, and we are calling bus of D. And what do we see in assembly? Let's look once again. We just filled the table, fill the pointer with offset to the table. Yes. Here we have this object constructed on stack. We are filling the table, and then we are calling it. RTTI is first argument. This object is stored on stack, so we are loading stack address to RTTI, and then we are calling bus of base reference, passing RTTI like pointer to derived to it, or like reference to derived. And then inside call function, we just loading from the table currently, and we just jumping whenever we load it. Great. So we expect some cost, but compiler can success in the virtualization. In reality, I broken this example to omit the virtualization, but you can think how to return the virtualization to this example. It is really easy. So dynamic polymorphism is not free. It introduces an extra level of indirection, at least conceptually. And now the question is, in this particular scenario, do we really need runtime polymorphism at all? If everything we need is just call function draw, we are not storing heterogeneous object in a container, we are not returning different types from a function, we only need a common interface and indirect invocation. Is there a way to achieve this effect without virtual functions? Try to guess, and let me show you the answer. Of course. Let's try to achieve the same interface without virtual functions, and this is the classic CRTP approach, curiously recalling template parameter. The base class is templated on derived. This one. Its draw method performs a static cast of this to the derived, because we know that this class was derived from object. And when we are deriving from object, we are parameterizing object with our derived type. Int public of object of int. Then this derived is int, and this static cast works and delegates to this draw function. Notice two things. First, the constructor is protected. That prevents accidental creation of the base class by itself. Second, there is no virtual destructor. Maybe that's correct, because this is not runtime polymorphism anymore, and there is no intention to delete through a base pointer. But if I still allocate int t dynamically and store it in a pointer to object t of int of t, then the delete through this pointer is everything fine, and not necessarily. So although we remove virtual dispatch, ownership semantics still matter, and CRTP remove runtime dispatch, but it doesn't magically solve lifetime issues. The important part is this: the call is now fully resolved at compile time, and if you look at generated assembly, the call is direct. Let me show you. This one. So we do have this call here and there, and this call interface that takes object tref and calls draw. And what do we have in our assembly? Oh, sorry, there is only executor here. But in executor we can see, okay, I think you don't need assembly here, because I don't think you doubt that this is direct call. This is direct call. Okay, you can see it. No virtual dispatch, no dynamic dispatch. But what you can see from executors, that everything just work. we are putting 42 here. We are calling via interface, and we are expecting OS string to be 42. So we've written something to this OSTring stream, and this something is 42. And in both executors, in Clang and in GCC, we see that test passed. So even with static dispatch, we do have a possibility to call something via the base class reference. No virtual table, no indirect jumps. Within a single call, this is strictly cheaper than virtual dispatch. So, CRTP removes the cost of dynamic dispatch. The compiler sees everything statically. It knows the exact type. It can inline aggressively. If you check Compiler Explorer, you often see just a direct jump, or even no jump at all because everything is inlined. Now, where else does CRTP shine? And one obvious area is when you want to inject reusable behavior into a class without paying for virtual dispatch. And this area is mixins, and CRTP is extremely powerful at CRTP mixins. Suppose we do have our int of t, and our int t defines only one primitive operation, say less, or maybe just operator less. From that single operation, we want to generate the rest of the comparison operators. Before the spaceship operator existed, this was a common technique. We define a template like comparisons of derived and just mix it into this class. And this class, comparison of derived, assumes that derived provides some minimal comparison primitive. Then it generates equal, not equal, greater, less or equal, and so on in terms of that primitives, in terms of equal function. And all comparison operators appear automatically once int of t derived from comparisons. And let me show you how this works. First, what would you put into the comparisons class? And the proper answer here is nothing. You don't need something inside the comparison type, because all you need is to define three operators like this and this and this to just support this mixin. And now we can safely call like this, and this will work because equal equal now comes from comparisons class. Of course, edge cases exist. For example, floating point nonce or infs will not fit well in this scheme, but that's the nature of generic programming. It works beautifully until the domain itself becomes tricky. And now what about, say, if we really want heterogeneous container and with CRTP we still cannot put all objects inside heterogeneous container with type erasure because CRTP do not erase types. If we do want a heterogeneous container of object, we still need virtual functions. But can we, with virtual functions, still benefit from CRTP? And let me show you one more example when virtual functions and CRTP are working together to make life easier. So this example will be about copying. And now let's switch back to our runtime polymorphism, and now let's find third error on this slide. Because we found two errors and I promised more, and now it's time for third. Suppose we introduce some copying into hierarchy, like this one. Is it a good idea? Copy constructors cannot be virtual, because constructors cannot be virtual. That's simply impossible in C++. So if you copy an object through a base type, you get slicing, which is completely bad. And the derived part is lost and everything messed up. And if your base class declares a virtual destructor but does not properly define copy and move operations, you're violating the rule of 5. And the rule of 5, if you're defining one of destructor, copy constructor, copy assignment, move constructor, move assignment, you need to define all 5. And here, with only virtual destructor, we deliberately, definitely, broken the rule of 5. Okay, and a polymorphic base class with a non-trivial destructor should very careful define or delete copying semantics, and otherwise you are inviting subtle bugs. So how do we solve generalized copying in polymorphic hierarchy? And the answer is not really C++ way, but it is practical. The traditional solution is to disable all copy move constructors and assignments and define virtual method to clone. Like this, virtual method clone returns pointer to object t, and it is const because it doesn't alter the current object, and it is pure virtual. And then every class redeclares clone as it wants. Like here we do have this one, and here we do have this one, and so on. So please note, this override is correct because you can override function specifying another but covariant, I would like to say, to generalization type, like object t here, int t here, because functions cannot be overloaded by return value. Then functions can be overridden by the return value. And this virtual function allocates a copy dynamically. And each derived class overrides this clone and returns this new int of t, new double of t, and so on. And this works, but there are problems. First, row pointers. We don't want row pointers. We want unique pointers here, shared pointers, yes. And second, boilerplate. Every derived class has to repeat some pattern. The mechanism is correct, but the repetition is annoying. And now we combine ideas. We keep runtime polymorphism because we need type erasure, but we use CRTP, like this mix clonable CRTP case, and this CRTP to mix in as a mixin to generate the clone implementation automatically. The mixin knows both the base and the derived type. It implements clone once using a static cast to derived, and suddenly all derived classes inherit a correct clone automatically. We still have virtual dispatch because clone is virtual in the base, but we removed the boilerplate from derived classes. And static and dynamic polymorphism are not enemies. They can complement each other. And in modern C++, we can simplify this further using deducing this. Now, the mixin doesn't even need the derived template parameter explicitly. We need only base here to derive. The type of self, like of this, of self, is deduced automatically. This is deducing this pattern. Please recall our lecture on lambdas when we explored it in some depth. And the implementations become cleaner and really more elegant, but conceptually nothing changes. We still combine runtime dispatch for the interface with compile time machinery to generate repetitive code. And this leads to important conclusion. CRTP can remove dispatch cost. CRTP can inject reusable behavior. CRTP can eliminate boilerplate inside polymorphic hierarchies, but CRTP cannot perform type erasure for you. You cannot put different CRTP instantiated types into a single stud vector of base unless base is a real runtime polymorphic class. And static polymorphism doesn't allow heterogeneous storage by itself. And that at some extent, yes, at some extent. And that is why, despite all it cost, runtime polymorphism is still necessary in C++. So far, everything looked nice and controlled. We combined CRTP and virtual functions with talked about clone, we talked about mixins, and almost naturally we arrive at multiple inheritance because mixins, you shall agree with me, are about multiple inheritance. Once you start composing behavior from different bases, multiple inheritance appears almost by itself. And now the question is, how does this interact with virtual functions and runtime mechanisms? Because as soon as we introduce multiple inheritance, the layout of object becomes more complicated, and that has consequences. Here is classical diamond problem. The E file and O file both derived from file, and EO file derived from both. And now suppose we have an EO file pointer and we cast it to E file pointer. Okay, this works, but we can even cast back. Yes, we can even cast back with this static cast. But then we try to convert our file pointer to file pointer. This line. Which file subobject do we mean? The one coming from E file or the one coming from O file? The compiler refuses because the base is ambiguous. And yes, we can fix it with virtual inheritance. We can qualify the path explicitly. But the ambiguity in inheritance graph propagates into casting. And this is not just about casts. There is very interesting symmetry here. If a cast from EO file to file, this line, is ambiguous and doesn't work, then catching file reference in an exception handler also will not work. But here is the dangerous part. With an explicit cast, you get a compilation error. Good. With an exception handler, you may get no error at all. The handler simply never matches. The program compiles. At runtime, the exception flies right past you catch block. Why? Because exception matching relies on RTTI, and RTTI respects the same inheritance rules, including ambiguity. If the base is ambiguous, the runtime cannot decide which subobject to bind to, and the handler is skipped. That is why I call this the symmetry between casting and exception handling. And let me show you how it works. I believe how it doesn't work in the case of exception handling. Okay, so you have this top of inheritance. You have this most derived class IO file, and it have two file subobjects. And then you throwing this exception and trying to catch it via file reference. And there is no compilation error here. This handler will just be ignored. Exception flies right past it here. And we will see runtime failure of our test, like this. And this is really dangerous, comparing to good old compilation error in case of like static cast. So if the conversion is ill-formed, then error handler is effectively useless. And there is another subtler case. RTTI does not ignore access control. If a class inherits from a base as protected or private, like here, consider I made this base protected, that affects runtime mechanism as well. In this example, input file inherits from file as protected, and inside the class we can static cast to file pointer, and that works because the conversion is accessible in the context. But outside the class, the same static cast fails, and what happens in exception handling? We'll catch file ref coach and input file object. There are two possible philosophies. Either the runtime ignores access control and sees the full inheritance graph, or the runtime respects access control and refuses to treat the base as accessible. Please think about this Write down maybe in comments here your justification. Why do you think so? What sentences from C++ standard make you think this way or other way? I will not give you an answer right here. So, access specifiers affect runtime type identification as well. And once you mix multiple inheritance, virtual functions, and RTTI, the model becomes significantly more subtle than the simple v-table story we started with. That's the real complexity of runtime polymorphism. So let's return to our diamond. Two classes derive from file, and the third one derives from both of them. We already know the problem. Converting EU file pointer to file pointer is ambiguous. There are two file subobjects inside, and of course, we know the classic solution, virtual inheritance. But as always, in C++, solving one problem introduces another layer of complexity. Let me show you. So, if both e-file and o-file inherit from file virtually, then e-file contains only one file subobject. Now the conversion is unambiguous. This just works. Great. Problem solved, is it? Or is it? And virtual inheritance changes much more than just ambiguity rules. It changes object layout, initialization rules, and even the structure of virtual tables. Because let's think a bit. If these subobject have this subobject of class file, and this subobject have this subobject, which one is this? Which was dropped? And from this layout, you may think that e-files this one was dropped. But this is not true, and this picture is not true. This file subobject can be anywhere, because both are dropped. Let's look at the constructors. With virtual inheritance, the virtual base is constructed by the most derived class, this one, not by intermediate classes. So even if intermediate classes explicitly call the constructor with some arguments in their constructors, those calls are ignored when constructing the IO file. Only the constructor call in IO file that initializes file actually runs. And that's a rule many people forget. The virtual base lives at the very bottom of the hierarchy and is initialized exactly once by the most derived class. And this already tells you something important. The language can no longer treat the layout as a simple stacking of subobjects. With a regular inheritance, object layout is simple. If e-file inherits from file, the file subobject is at a fixed offset inside e-file. The compiler knows it at compile time. Everything is contiguous. Pointer adjustment is trivial. With virtual inheritance, that guarantee disappears. The location of the virtual base inside the most derived object is not fixed in the intermediate class. The offset may depend on the final derived type. That means conversions to the virtual base often require runtime adjustment, and that implies additional metadata in the virtual table. And now things become really interesting. With virtual inheritance, the virtual table is no longer just a list of function pointers. It also contains offsets to virtual bases, offsets to the most derived objects, RTTI pointers, and other internal machinery. When you perform a virtual call or access a member through a reference to a virtual base, the compiler may need to load a pointer from object, follow it to the virtual table, read an offset, adjust the pointer, and only then access the field or call the function. Even at high optimization levels. Let me show you this example. It is truly interesting. So let's look at it. Great. So we do have this base and we do have this derived, and this call virtual calls nothing. It just addresses d.a. We just need to somehow take derived and address a field from base. Looks like simple, but base is virtual base, and nothing simple if you have virtual bases. So let's look at this assembly. And this assembly is non-trivial. So here it is. First, we did something. Presumably we loaded virtual table. Second, we did something else, like we addressed this table, something we loaded from this table with some offset, and put result here. And then we did something even less trivial. We put this offset calculated from virtual table minus, in this case, 24, and added what was loaded from here to our virtual table, and then we do have our A field. And this inefficiency is inefficiency of virtual bases. In a simple single inheritance, a virtual whole may be just one indirection and sometimes even devirtualized completely. In the presence of virtual inheritance, accessing even a field through a hierarchy can involve multiple pointer adjustments, 2 or even 3 memory reads in the worst case, and calls are 2 or 3 memory reads in the worst case. And all of these just to reach data member that physically sits inside a same object. So virtual inheritance solves the damage problem, but the price is significantly increased complexity in object layout and dispatch machinery. And this is the part of runtime polymorphism that most textbooks politely skip. And here's a question I really like to ask in interviews, especially for senior level engineers. Why does dynamic cast exist in the language, and what exactly does it do? And the first part of question is relatively simple. The second part is where the things get interesting. And please pause the video for a moment and try to write your own answer to this question. Imagine you are on my interview and try to answer honestly. You may even don't write this in comments. You may write this in comments, but you may not. Just try. What do you think? Without looking anywhere. Just you and me. Stable. Okay, I believe you did. So many people say, maybe you also said, well, dynamic cast is not much needed in the language. Why not compare types with type ID and then use static cast? But that does not solve the real problem. The key issue is pointer adjustment in the presence of multiple, and especially virtual inheritance. The offset between sub-objects is not known statically. You cannot just reinterpret the pointer. You need a runtime knowledge of the object's layout. And the dynamic cast provides precisely that. Dynamic cast exists in the language only because virtual inheritance exists in the language. And this is why dynamic cast exists. And what dynamic cast precisely does. There are essentially 3 canonical forms of dynamic cast. First form is dynamic cast to void pointer. And dynamic cast to void pointer converts any polymorphic pointer to a pointer to the most derived object. There is exactly one most derived object. That case is conceptually simple. And second one, casting to a derived type, especially through virtual bases. This is a checked down cast. The runtime verifies that the object is indeed of the requested type and adjusts the pointer correctly. And third, casting to a sibling type, a type that is not directly related in the inheritance chain but shares a common base. And this is the most complex case. The runtime must navigate the RTTI graph to determine whether such a path exists and how to adjust the pointer. Upcasts to base types usually don't need dynamic cast at all. A static cast is sufficient. I believe here we do have a good example, yes. So let's look at it. We have a dynamic cast to IO file pointer, dynamic cast to input file pointer, dynamic cast to output file pointer. This is sibling type, yes. We really do have IO file type. And we upcasted this to input file, and then we sibling casted this to output file, and everything works. And then dynamic cast here to output file pointer, and then dynamic cast to void pointer. And bingo, we have all tests passed, and now we see the dynamic layout of our object and all its sub-objects. We see where the most derived object lives. This is cast to void with. We can see that the most derived object is indeed the IO file sub-object, and we can see where IO lives and inf lives and out lives. Okay. And now, which of those forms is more expensive? The cheapest one is the typically dynamic cast of void. At the runtime already stores information about the most derived object, and the adjustment is straightforward. Casting to a known derived type is more expensive because the runtime must verify the relationship and possibly adjust across virtual bases. And casting to a sibling type is usually the most expensive case. The runtime may need to walk the inheritance graph, follow RTTI structures, checking for ambiguity and accessibility. I hope there is something useful here on Goldbolt. Yes, definitely. So let us look at those functions in assembly. This is to most derived, this is to child, and this is to sibling. And what assembler will we see? To most derived, like nothing fancy, just a bunch of assembly instructions. To child, oh, call of dynamic cast with some processing of result. And what about to sibling? The same, call to dynamic cast with some processing of input arguments and result. You can see here -1 and here -2, and this makes a difference between upcast and sibling cast. So upcast and sibling cast mostly from this assembly same, but what are dynamic cast internals? And let me show you. If you look at the implementation, you will see, let me show you, this is typical C++ standard library. I took one from Android, but you may take what you like the most. So what do we see here? We see here walk object, and walk object is dynamic cast helper, and in Russian walk means wolf, so it grows. And we see that walk object calls itself recursively. I believe it calls its pack recursively. And once again, and again, and I just tried. I prefer bass. And then we can see the dynamic cast. Yes, here. And here we see the hints here. Yes. And -1 means no hint. And that is one -1 is worse than -2. -2 means source is not a public base of destination like cast to sibling type. It's like hint. And dynamic cast basically calls walk object and holes. And again, and adjusts pointer, and again walk object. There are too many walks in the room. In complicated hierarchies, this can involve recursive steps, a ton of recursive steps. Conceptually, dynamic cast in the worst case is much closer to in cost to throwing and catching an exception than to a simple static cast. A static cast is just pointer arithmetic, often a single instruction. A dynamic cast may involve recursively walking the runtime type structures. And here is subtle part. According to the standard, dynamic cast can be resolved as a simple static conversion. If it can be resolved, it behaves as such. So in the trivial cases, compiler may optimize it heavily. But the moment you rely on real runtime checks, especially with virtual inheritance, the cost is significant. That is why dynamic cast has a very specific and narrow justification: safe navigation of complex polymorphic hierarchies when pointer offsets are not statically known. And that is also why you should never ever treat it as a casual replacement for static cast. Okay, so let's revisit our motivations. We said that we need runtime polymorphism when we want indirect calls through a base interface. Probably this is CRTP. We want to join different types depending on runtime conditions. We want heterogeneous storage, and sometimes the fourth motivation, sometimes we want to reuse implementation, especially in diamond-shaped hierarchies. And now look carefully. The first and the four items are a bit suspicious. Reusing an interface often looks a task for CRTP. Reusing implementation that often looks like mixins. In both cases, we might not actually need virtual functions at all. The second and third motivations are slightly harder to eliminate. So the question is, can we do something about those gray areas, like gray bullets, without paying the full cost of classical runtime polymorphism? And let's recall Sean Parent's famous example. We want a stud vector that stores different types by value. We want to push this and that, and then we want to iterate and call draw for anyone. In the classical approach, we introduce a base class with virtual functions, but immediately we lose value semantics. We no longer store objects, we store pointers, which means reference semantic. We need clone, we need dynamic allocation, we need ownership management. The simple looking vector suddenly becomes a vector of pointers, or vector of smart pointers, or vector of smart pointers with shared ownership. And that changes everything. Dynamic polymorphism effectively forces reference semantics. Copying becomes cloning. Assignment becomes pointer manipulation. Heap allocation becomes unavoidable. And once you allocate on the heap, you must decide who owns the object. Just throw pointer and hope for the best, or maybe unique pointer, or maybe shared pointer. And this quickly turns into ownership hell. And there is another issue. When you store pointers in a container, you no longer have a single contiguous array of objects. You now have a container of addresses pointing somewhere else in the memory. And that creates what Sean Parent calls incidental data structures. You did not intend to build a graph, but by introducing a pointers, you often accidentally built one. Two objects referencing the same heap allocation already form a graph. Just reverse those arrows and you will get a tree, yes? And that complexity was not part of your original design. It was introduced by the mechanics of runtime polymorphism. So, how do we escape this? There is really one main idea: hide runtime polymorphism inside a value type. We create a wrapper class, say object T, that can be constructed from any type satisfying some runtime concept. Internally, it stores something type erased. From the outside, it behaves like a regular value. Now, how do we implement this? And there are essentially two strategies. One is to invert polymorphism, reduce it to overloading or some form of external dispatch, and the other is to manage dispatch tables manually, essentially implementing our own type arrangement. Let's start with the second approach, because it is more general and reveals what runtime polymorphism really is under the hood. And now let's try to manage dispatch tables ourselves. This is inspired by a well-known talk by Dionne, and the problem is simple to state. We want a common interface like drawable, but we want to preserve value semantics. We want to write std vector drawable document and push back this int and this double that both implement draw method. No base class pointers, no manual clone, no exposed heap allocation. From the outside, this should behave like a normal value type. And the idea is surprisingly simple. Inside drawable, we store two things: a pointer to a small manually constructed vtable and the void pointer pointing to the stored object. The constructor is templated. When we construct drawable from some any, we select a vtable for any on the heap, and the draw function simple calls virtual table pointer draw pointer or string. So we have recreated runtime polymorphism but manually. And here is the important shift. The heap allocation is now encapsulated inside drawable. From the outside, it behaves like a value. We no longer leak pointer semantics into the user's data structures. The vtable is just a struct of function pointers, one for draw, one for delete, and then we define a variable template vtable for t. For each t, we instantiate a small static table with two lambdas, one that casts void pointer back to t star and calls draw, and one that deletes the object. And two modern C++ feature makes this elegant: variable templates and the automatic decay of captured lambda to function pointers. So for each concrete type, we generate exactly one tiny dispatch table stored in global memory, like normal vtables do. And this is essentially what the compiler does for virtual functions. But here we control it manually. And now, if you were paying attention during our allocator lectures, something should make you uncomfortable. Look one more time. Like new and delete. We are allocating on the heap for any stored object. If this drawable lives inside std vector, fine, but what if it lives inside PMR vector with a scoped allocator? Does our internal allocation respect that allocator? No, of course. So the moment we encapsulate runtime polymorphism, we must also think about allocator awareness and small object optimization. Otherwise, we just moved the ownership problem. We didn't solve it. And this is where more mature libraries come in. And I would wholeheartedly recommend Nick Kelbon's Any library, a very nice example from one of subscribers of my channel. and my colleagues here in Moscow. And it generalizes the DNA ideas. Basic N is parameterized by an allocator, a small object buffer size, and a list of methods that define the runtime interface. Internally, it stores a pointer to a table, a pointer to the value, a small buffer for SSO, and the allocator. So we get type erasure, small object optimizations, allocator support, and customizable method sets. In other words, a production-grade version of the simple drawable sketch. Okay, and usage looks almost like a Rust trait. We define a method wrapper. For example, draw, it specifies how to invoke draw and concrete type, and then we define it using any drawable is any withdraw, and now we can construct any drawable from int, double, or any type that provides draw. And we invoke it via invoke draw of option. Conceptually, we have implemented a trait-like abstraction in C++ without language support, just in library. We preserved value semantics, we hid runtime polymorphism inside, and we avoided exposing pointers and ownership to the user. And this is the key idea. Runtime polymorphism is not the enemy. The problem is exposing it directly. Once you encapsulate it properly with type erasure, SSO and allocator support, it becomes a powerful and safe, relatively safe tool. And let me ask you a question I like to give to strong students. Stud function stores a closure. Sometimes stud function stores a closure on the heap, sometimes using small object optimization. Do you think it supports custom allocators? It used to have allocator relate machinery, but today effectively it does not. Why? We just spent quite some time building a type-erased wrapper with a web table, optional SSO, and allocator support. It looks perfectly doable at the library level. So why did the standard library more or less give up on allocator support in stud function? And this is not it is impossible. It is because once you mix type erasure, allocator propagation rules, copy, semantics, and exception guarantees, the design become extremely fragile. Probably. Let me show you the quote from the CP reference. So, quote is: stud function allocator support was poorly specified and consistently implemented, and some implementations do not support useless allocator construction at all. Some provide the need constructor overloads, but ignore the supplied allocator argument, and so on and so forth. It's just funny to read this, but this is not the answer to the question. Okay, some implementation did it wrong, but let me show you. I can manually do it right, just mixing Kelbon's library with some DNA ideas. And the idea is simple in principle. Instead of relying to the standard stud function, we can build our own basic function and internally just our type-erased container. And the call operator simply forwards invocation into the type-erased storage. In other words, stud function becomes a thin wrapper around a customizable type erasure engine. And technically, this works, and library-wise, this might be done elegant. So again, how do you think? Why didn't the standard just go this route? I will not give you an answer. Please write your answer down in the comments in this channel. Let's have some great discussion on this. Okay, now we should pause and reflect. What have we been doing for the last several slides? We manually rebuilt virtual dispatch tables, type erasure, clone semantics, allocator support, small object optimization. In other words, we started replacing language mechanisms with library abstractions. Is that a good idea? When you use built-in virtual functions, the compiler understands the semantics. It can devirtualize. It can optimize across calls. It knows the inheritance graph. When you roll your own dispatch tables, the compiler sees only function pointers, no devirtualization, no structural understanding. Now, imagine going further. How would you support something like virtual protected bases in your custom type erasure? How would you support dynamic cast? How would you integrate with exception handling and RTTI? Are you really ready to re-implement that entire machinery by hand correctly, portably, and efficiently? And type erasure is powerful. But every time you step away from language-supported runtime polymorphism, you also step away from decades of compiler engineering baked into it. And that is the real trade-off. And let's go back to Sean Parent's problem. We want a stud vector of object of t here. And we want to push integers, strings, user-defined types, and we want value semantics. Is there a language mechanism that already allows us to create a common interface between primitive types and user-defined types? Yes, there is. We've already seen it. Overload resolution. Primitive types and user-defined types can participate in the same overload set. That's a fully language-supported mechanism. So maybe the interface should not live inside the objects at all. Maybe it should live outside as a set of overloaded free functions. An overload set can support anything, and if this exists and this exists, the compiler knows how to select the correct one. But can we store now? Second bullet, hidden storage. Can we store different types in a single container while delegating to that overload set? And now we are back to type erasure, but this time we use language facilities instead of replacing them. We introduce a small runtime concept and store a pointer to it internally. And from the outside, object T behaves like a value. Inside, it delegates to appropriate overload. And what is concept T? Instead of forcing user types to inherit from a base class, we introduce, like reversing the polymorphism, we introduce a small runtime concept and to wrap arbitrary types into a model, which is deriving from concept which have virtual function interface. The concept defines minimal runtime interface, destructor copy, and the draw method to delegate to overload set. Then we provide the templated model of T that implements this interface for any T. And notice, we are not replacing virtual functions. We are using them in private part of our class. And now let's define the model. The model is trivial. It stores a T. Its copy function performs a deep copy. Its draw simply calls a global draw overload. And that's all. We use overload resolution instead of building our own dispatch tables. We let the compiler do what it already knows how to do. And now we can store integers, strings, user-defined types, even nested object instances, all by value. No exposed row pointers, no manual dispatch tables, no incidental data structures. The heap allocation still exists internally, but it is encapsulated. So the container itself remains conceptually simple. And this lecture has one of the few open endings in the course. Dynamic polymorphism is not simple, it is also not obsolete. Trying to remove it completely often leads to rebuilding it manually, usually in a more fragile form. At the same time, treating it as trivial is a mistake. It interacts with RTTI, exception handling, virtual inheritance, allocators, ownership, optimizations. We saw two common misconceptions. First, that dynamic polymorphism is unnecessary. Second, that it is simple. It is neither. The language gives us several ways to approach it. Classic virtual functions, CRTP, manual type erasure, overloaded based design, and your move is next. With newer language features, reflection, code injection, metaprogramming, this space is still evolving. There is no final answer. But there is some bibliography. If you want to go deeper, please start with Sean Parent's talk on runtime polymorphism. It is brilliant and you must see it. Also, Dionne, Back to the Basics, and Arthur Woodwire, Dynamic Cast from Scratch is also excellent, especially if you want to understand how expensive RTTI machinery really is. And also please note C. Brand's talk that connect dynamic polymorphism with newer metaprogramming ideas. And runtime polymorphism is one of those topics that never quite goes away. And starting from the next lecture, we move into multithreading, where many of these questions become even more interesting. That's all for today. Thank you, everyone.